Now, this is an ALDI induction cooktop, and I kind of wanted to know what was inside one of these. So, yep. Screws, just taking them out, and this comes right off, I think. Yeah. So, held on by something. Go. Ooh. Ooh, I wasn't expecting that. Okay, the glass is separate and everything else is on the base. Okay. Yeah. Okay. That's the back of the glass there. It's got this sort of textured pattern. Yeah. What do you know? So you can see it. It's ABS. So not the high-tech plastic I was thinking. It's pretty interesting. So it comes in mains through here. Inductive ceramic bead there. Inputs. Looks like, what's that? Looks like some sort of, big old capacitor, 8 microfarad, and is that some sort of relay, I think? Looks like a relay. Then we have switch mode power supply, another big capacitor. This looks like some sort of inductor, that could be capacitor as well. Oh yeah, and then we have all the capacitive buttons up here, capacitor controls. 7-second display, and under here will be the main power circuitry, I imagine. And you don't. Go just like you. There we go. Now we're out. Ah, yep. What's that? So that is some sort of bridge rectifier, it kind of looks like that, would be the main switching, right there. Oh yeah, bit of thermal compound there, the white stuff. Too bad. Both it's capacitor, they're both capacitors. That's a main inductor, so this is some sort of LC, how are they connected? It's done the main micro in there, this port here. How's this held in? Oh, a couple of screws. There we go. And let's have a look. Work that out. Oh, yep. We're a multiplexing chip, and that just runs all the LEDs and the 7-segment display. And then we have here would be a couple of sensors. So that kind of looks like a reed switch there. And that might be a thermal switch. So one of these is 2 pins each. So one of these is detecting if a pot is on there, and the other one would be to over temperature, I suspect. Oh, yep, there we go. It's just in there, little silicone thing with 2 little sensor bits. I'll have to clean that up a little bit later on. Oh yeah. Ooh. Those magnetics. What are these? I haven't opened one of these up before, but that looks like, I don't know. They're ferrous. They must be for field concentration. It must be to concentrate the magnetic fields through the material, and that's just a backing plate, which is this magnetic at all. That's actually not magnetic, so that isn't actually involved. That's just probably for heat shielding to prevent the plastic from getting hot. That's polypropylene just over there. It's a reasonably high temperature plastic, so that's okay. But yeah, that prevents the plastic from melting. The real magnetics is done by this sort of, sort of ferrous, crystal-y material. I've seen this before. Kind of reminds me of sort of iron magnets. Interesting. But yeah, no, this is what I think it is. This might be Litz wire, a type of wire where the individual strands that come through here, they spend an equal amount of time on the outside of the wire and on the inside of the wire. Sort of balances out the inductive loads. Ooh. Is that a broken strand I see? Ooh. What are they? I think I see broken strands. Just in there. Yeah. This one's had a bit of a interesting life. Some sort of splicing they've done. Because these are just rings. They're not actually spiraling in. So the way they do it is they're spliced. They're spliced. You can see these rings. It's not a spiral. They're just rings. So they're spliced in. Splicings along the edge there. So it's a bunch of inductors in parallel, is it? How are they done? Oh no, just tap in the middle. Yeah, there's a bunch of inductive coils all in parallel, because that's like a bus bar along there. So that goes along like that. And it comes, and it goes, yeah, one layer down. Ah, so it's a bunch of inductors in series, and they spiral in for each ring into the center where they can't, this cable here, and onto the board. Okay. Now that is just a standard fan. Yep, nothing wrong with it. Wrong G-Far electronic, very nice. 18 volt, ooh, odd voltage, but looks fine. Sleeve bearing, yeah, pretty standard. So yeah, let's have a look at this. Mains cable, pretty standard. What's the temperature on that thing? 1 squared. Oh yeah. It's a nice big ferrite bead. Oh yeah. I'll do a bit of analysis on these boards and I'll be back in a bit. So here's the main board. It's a single layer PCB and it's got a bunch of through hole components on the top here. And we can see the traces on the bottom. So we have the live that comes in through here. It goes through a fuse over to this side here. We have a MOV across that with a 820k resistor there, just to discharge this big capacitor, which is across the live and neutral. Then it comes into this relay over here, which is switched by this microcontroller through, I believe, yes, this MOSFET. After that, it comes and goes through to this full bridge rectifier. A schematic for, oh yes, here we go. So it's a Fagor 20 amp glass passivated single phase inline bridge rectifier. It's made, I believe this is a Korean thing actually, but yeah, it does. This is a D20XB80. So it has a peak recurrent voltage of 800 volts and a max RMS voltage of 560, and it's a 20 amp thing, so it's pretty well rated. And it's attached to this nice big heatsink. Now off that bridge rectifier, on the positive line that goes through to this large inductor here, I've been able to measure this, and then it comes down into this rail here. On this rail is attached one end of the main coil, just this one over here. And then the other side, as it comes through, it's attached to this capacitor across these two leads. And this, I believe, actually, a bit of bits here. Here we go. So that capacitor here is this capacitor here. So 8 microfarad, 400 volt. And this is the large inductor that's on the board L1. Now, apart from this, there's also a large-ish capacitor, which is this one here, a 0.3 microfarad 600 volt, which is across these two leads of the IGBT. That is the main switching element. This IGBT is from Trino Technology. It's a 1350 volt field stop trench technology. It's quite good. So yeah, 1350 volts, and it'll do 40 amps, you know, those are always a bit inflated, but yeah, 40 amps at 25 degrees C, that's pretty good. Anything else? Yeah, it's quite a good one. So yeah, they're using a single one of those attached to this large heatsink, and that is switching across negative of the bridge rectifier and the high side, I guess, of the main coil. This main coil here, so it's one of these, and across with capacitor here. So effectively you have a capacitor and an inductor here, which act as a bit of a filter, power filter, to sort of reduce the amount of noise coming off this big switchy thing. And then you have a LC oscillator thing that is driven by this IGBT. Now I have a few things here labeled drive sense A and sense B. Those are going to this microcontroller here. There's a little micro in there. It's a little 16-pin no name because it has no markings. So fun. So we have the mystery microcontroller, and we have a few things attached to it. So first of all, we have some temp sensing. So over here we have a few connectors. So this one here is your main connector to your front board, which handles the UI, the user interface board, and this one here is for a temperature sensor of some description. I'm not exactly sure if it's a thermocouple or thermistor, and that plugs into here through a couple of capacitors, it looks like. Yeah, there's a couple of these capacitors with it and a resistor. We have a 5-volt input. We have for the front panel sort of user interface, we have a I2C interface, so SCL, serial clock, and serial data, SDA. We also have a buzzer, so this buzzer here is driven by that pin there, and we have the IGBT drive pin, and that goes from here around here and into this here, which is a discrete IGBT driver, which is made of, I think, P and N channel MOSFETs. So I'm not exactly sure. I can't read the labels due to the conformal coding of this board. And finally, we have our Sense A and Sense B. Those are connected. Those are connected through large resistor chains. So this one here is an 800K resistor chain. Obviously to add the voltage tolerance of each of these resistors in series, so that way they can resist presumably 1, 2, 3, 4, 5, 6, 7, 8, what, 600-ish volts, because they're about 75 volts each. And we have a 400K resistor here, well, 400K made of two 100s and a 200K there. And those connect into the 16-pin mystery chip in these two pins here. I haven't really looked into a bunch of the other pins. They don't seem to do main driving functionality. Some of these are sensing, so one of these pins would drive the relay over down here, and another one of these pins, I suspect, interacts with the power supply. So the main power supply is here. It's one of these little 8-pin dips, and it drives a buck converter. So this little well, it's sort of a transformer here, and it bucks the voltage down to 18 volts. And then in here is a little TR92 package, I believe, which is a linear regulator, and that provides the 5 volts for most of the microcontroller circuitry. So yeah, that's pretty good. That's pretty much all of it. Yeah, okay, let's move on to it. So this is the main control board, well, it's the main user interface board that sits underneath the glass. It has little capacitive buttons, these little springs here, and a bunch of little LEDs, and this 4-digit 7-segment display. Now underneath, we find a very interesting thing actually. So we have this microcontroller here, and I don't know if you can see it, but that microcontroller is made by BYD. This has been translated from Google, from their datasheet, but it's an 8051, so Intel 8051 based microcontroller, and it has a lot of capacitive buttons, which it needs to, because it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 buttons, so it needs them, and each of those buttons has a little SMD resistor right here. It's a 4.7K. And then it drives the LEDs, all these LEDs, in a multiplexing array. So as far as I can tell, the main brains is this chip here. So this actually drives the induction cooktop, essentially. And I suspect this chip here just provides a user interface and maybe the timer. So it'll tell this chip what sort of power level to do and when to turn it on and off. And then this chip itself handles all the driving, all the temperature sensing. It also handles the safety features, so it has the relay right there, and it can it actually has in underneath this little bit of silicone is actually a thermistor. It's marked RT1, so it actually measures the temperature of this IGBT to prevent it from overheating, which is quite nice. Apart from that, there's good isolation slots in this board, so you can see on the top here all the power traces going to the IGBT have a nice isolation slot in them, and that prevents the tracking, so that little pin there is nicely isolated from the low voltage stuff around here. And there's lots of little bits of silicon. I suspect this is for thermal coupling, because there's little temperature sensors around the place. So this is to sort of monitor temperatures. It's quite nice. So yeah, that's the inside PCBs. This is the main induction coil, and you can see it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 rings. Interesting. So it's 13 rings of this multi-strand sort of copper wire, and you can see they're rings, but they're connected, if you get the angle right, in here. There are little connections between each layer. So obviously this is a coil. It's just broken up into rings that are joined in a point around here. So some sort of splicing thing, I suspect. It's quite well done. And on the back side, we have this ferrous material. They're not magnets, but they are magnetic. So magnets do stick to them. And this is to, I guess, concentrate the magnetic fields in this sort of pattern. Obviously the field lines, when they go through the pot and then back in, and then out the back and then come in, this helps them stay relatively close to the coil and increase their strength. So that's quite good. I kind of just rambled on about that. So now I'm just going to put this back together and test it out. Okay. Let's give it. Good yet? Ah. I suspect this is why. Okay, I probably should have expected that. This was, after all, thrown out. So, it not working, not a surprise. Okay, first thing to check is this fuse here. Okay, quick, just gonna check. Uh-oh. So that works. Here we go. Ah, yeah, we're out. It is. That just it. Pretty fucked up in there. Ugh. Focus. 15 amp, 1.125 volt. Ooh, 10 amp, 250 volt. Okay. DaVinci decided that my audio doesn't exist for some parts of this video. So what I did was I replaced the thermal fuse there with one I already had, which happened to be exactly the same actually. It was a 15 amp, 250 volt fuse that triggered at 240 degrees Celsius. Ooh, it works. Here we go. Oh yeah. How's this gonna work? Ooh. How does this work? Oh, it actually does temperature. Oh yeah. Let's try 160 degrees. Right, okay. Oh yeah. That really works, eh? Fantastic.